In this video, we'll be talking about some graphical interpretation of solutions to systems of linear equations. We saw prior that one way to solve a system of equations is to graph both lines and find their intersection point. In practice, though, three things can actually happen, each of which tells us something about the solutions of the system. First off, we have sort of three possibilities. So the first one is that either the two lines can intersect at one point, and what that would look like is that would basically be saying what? You plot both graphs, maybe one looks like that, maybe one looks like that. Well, then we know that there is thus one unique solution. On the other hand, the two equations could represent the same line. What that would look like is you do one equation that looks like that, and then when you try to graph the other equation, you end up with the exact same line. What that would mean is that there are infinitely many, thus non-unique, solutions. Finally, if two equations represent different parallel lines, that would look like, so we have one line and then graphing again, we'd have another line, a parallel line, and since they never intersect, it follows that there is no solution to the system of linear equations. So, as an example, let's go ahead and graph the lines, sketch the graph of each of the following systems and see what we can learn better about number of solutions from this. Here, if we solve out for this one, we have that this is the set of give me a moment. That is going to be the line y equals 2/3 x minus 1. If we solve out this one, however, we end up with y equals 2/3 x, but this time it's going to be plus 1 if we solve out. Which means what we have here is we have first, the first equation is the line that goes through -1 and has a slope of 2/3, so up 2 over 3. So that would be a point. We know that it intersects at -1, and so it looks like that. On the other hand, this line is the line with slope 2/3, but it starts at +1. So over 3 up 2. And so what we have is we have two parallel, if I was better at drawing, lines, which means there's no solution here. Okay. Here, if we do this, this first one is exactly the same line we saw before, which is y equals 2/3 x minus 1. This one, however, is now the line y equals -1/2 x minus 5/2, or plus 5/2, sorry. So plus 5/2. Well, we already graphed that first line. That first line is 1, 2, 3. And here we so that was what? 1, 2, 3, so we were there. So it looks like that. However, here this line is going to be at 5/2, so 1, 2, so that's 2.5. And then we go down 1/2 every time we go over, right? So there, down 1/2, so there. And so it looks like, hey, look, we actually have a single intersection point, so there's one unique solution. Finally, if we graph here, again, we have the familiar line y equals 2/3 x minus 1. And then we have y, but this time it's 2/3, it's again going to be 2/3 x minus 1. Which means that here we actually have a graph of the same line, which kind of makes sense because if you multiply all of this by -2, you get the exact same equation down there, right? And so, really, these are the same equations, namely it looks like that. Both lines look like that. And because you just get the same line, any points on that line will be a solution, which means you have infinitely many solutions. Infinitely many solutions. Now, that being said, we have a name for these types of solutions. If you have at least one solution, so that includes infinitely many, then the system is called consistent. While if you have a system with no solutions, such as this one, it is called inconsistent. So what that means is that we have up here that this is an inconsistent system, while these are both consistent. Now it's time for you to try. So go ahead and graph the system of linear equations to try to solve it. And then based on the graph, determine the number of solutions and state whether the system is consistent or inconsistent. On the count of 3, I will reveal the solution. 1, 2, 3. So if we solve the top equation out for y, we get y equals 2/3 x plus 2, which means you're going to get this top line when you graph it out. Here, y equals 2, so the bottom equation is y equals 2/3 x plus 3/2. Graphing that is going to give you the bottom line. Namely, you get two parallel lines, which makes sense because you have the same slope, which means that there is no solution, thus the system is inconsistent. Now the question is, what happens when you're actually trying to solve these equations? So I'm going to solve this using elimination to see what happens, okay? Because when there's infinitely many or there's an inconsistent system, you may wonder, what does that look like? What happens in your solution? So solving this out, let's go ahead and do elimination by multiplying the top equation by 2. So we have 2x minus 4y equals 6. And then we have negative 2x plus 4y equals 1, which means we can eliminate the x's. But when we do that, the y's also get eliminated. And so we end up with 0 over here. But on the other hand, we have 0 equals 7. Well, since that can't happen, this has no solution. That is, this is an inconsistent system. Now it's time for you to try an example that's similar. Go ahead and try out this example. On the count of 3, I will reveal the solution. 1, 2, 3. So we see here that if we multiply the top equation by 2, then we're able to eliminate the x's, but the y's also go as well, in which case we end up with 0 equaling 11 on the other side, so there's no solution, aka the system is inconsistent. Let's do one more example. Let's solve this system of linear equations. Solving this system of linear equations, what we have here is, let's go ahead and multiply the top by negative 2. If we do negative 2 in the top, what we end up with is negative 4x minus, plus 2y equals, so here I multiplied by 2, and then equals 2. Here you have just the same equation. Here I actually multiplied by negative 2, so that should be negative 2 there. Well, now everything actually eliminates. That's 0, and that's 0. Namely, we end up with 0 equals 0. This actually is still a consistent system, because that is true that 0 equals 0. But what does it mean? Well, it means these lines are actually the same line. So this is the infinite solutions scenario, which means that we need to do something a little clever. So here's what we do in this scenario. We go ahead and we're going to take, since these are the same equations, we really just have the one equation, 2x minus y equals 1 now, that we're working with. We're going to go ahead and let x equal a, which is some real number. And then what we have is that y, if solving out, we would have that y is thus equal to 2a minus 1. So we get the set of ordered pairs a, comma, 2a minus 1, where a is some real number, where a is any real number. And that's our actual solution. And you may say, well, that's a weird solution. Well, what it's saying here is a can be any real number, so pick your favorite number a and plug it in. That will still be a solution. Namely, we get an infinite number solution since a could be any of the infinite number of real numbers that we have. Okay? And now, once again, it's time for you to try out an example. So go ahead and solve the system of linear equations given there. On the count of 3, I will reveal the solution. 1, 2, 3. So here you go, if we multiply the first equation by 8 and then add the equations to eliminate the x's, we also eliminate the y's, and we also eliminate the constants, giving us 0 equals 0. So this is a consistent system. However, it's the same line, so this is the infinitely many case. So we have x, we let x equal a. That means using the second equation, negative 4a plus y equals 3. Solving out, we get y equal 4a plus 3. So a comma 4a plus 3, for a, any real number, is going to be our infinite number of solutions. For more practice in working with the graphical interpretations of these solutions, be sure to see the textbook, pages 486 and 487. In our next video, we're going to talk about a few more applications of linear systems.